the Graduate Center. And one of the papers I'm most proud of, Mike and I wrote, and the title is Evaluating Rational Functions, Infinite Precision is Finite Cost, Tractable on Average. And that was sort of, for me, an impetus to work with Mike, and then later with Steve, when we started to design our model of computation over real and complex numbers. So that was our entree to start working with Steve on this model, which you've heard about a little bit. And what I'd like to say, which is a little different than what Nancy was saying, mathematicians, there's another approach to simplifying. Another approach is actually to take a problem and put it in a bigger domain, and maybe you can see more in a bigger domain. So in computer science, one of the key problems is the NP-complete problem over bits, over discrete structures. What we did is we put that problem, the NP-complete problem, we show the generalization over any field, which included the real numbers and the complex numbers, with the idea that you might be using other kinds of mathematics to attack the problem. So that was an approach that we did with our first paper. Later on, what was very important in the work, let me just point out Jim Renegar's work on, the NP-complete problem is very easy to state. A finite system, a polynomial system is NP-complete, basically. That to decide whether or not it has a solution is NP-complete. And Jim gave a fantastic result, at least showing that problem over the reals was actually exponential. So it's a very nice analogy to the classical problem over the integers that came out of that. So the work actually expanded, and Felipe Kuker, where are you, Felipe, who came in and really developed, we wrote this book together, the four of us, and then Felipe developed the condition number area, which was the next stage. So there's a whole lot of things came out of this, and it all started a little bit with my getting woke about women and math. So thank you, Mike, for actually, that changed my life when I went to New York and worked with Mike on this math, and it got me right back into mathematics and doing work we did, which, thank you so much, Mike. It was really fantastic. So, I mean, okay.
I met Steve, it must have been 1962. So I don't know if that's 60, 70 years or whatever, but it's a long time. A long time ago. Can you hear me? Yeah? Yeah. My voice is very low, and my whole expertise in this new modern technological world is very, very weak. So what I did is I prepared foils. But there's no foil projector here. There's only something you have to plug into a computer, which I don't even have with me. So this is going to be a different type of talk, a lot of words, and maybe not so much where I'll try to draw a picture on the board. First, I have to thank my co-organizers here, Lenore and Indika and Michael, and they did all the work and prepared the meeting, and I lay in a bed in the hospital, immobile. So I had very little to do with preparing the meeting here, and my co-organizers did a great job, and I'm ready to take all the credit. The next thing was, I got an email from, let me see if I can remember his name. Jair Koilar. Would you stand up, Jair, please, everybody? I'm going to tell a story that involves things that Jair knows about much better, but it's not going to be complete in any sense. So you should all go and talk to Jair about it and find out more. The story concerns a meeting in Bahia, Brazil in 1971. And at that time, repression in Brazil was very, very strong. And there was actually a student at IMPA, Alexandro Magalhães, who had been arrested and tortured, and his wife as well, and she was still in jail. And the senior mathematicians, I had just gotten my degree, so I was not involved in the initial stages of this at all, but the senior mathematicians decided they were going to try to do something to help this student. And maybe ultimately it was going to be on the order of putting together a petition to the judge to let his wife out of jail, partly on the basis that she was being held in jail longer than Brazil's constitution would specify as the maximum permitted. So that was the situation there, and I think the mathematicians got very involved in it. Even as the group got larger, people started to arrive in Brazil from France and other places for the mathematical meeting that was going to happen in Bahia, and there was talk of at least putting together a petition to the judge to let Dulce out of jail. And I think the Brazilian mathematicians started to get very upset because the repression was so hard that they were afraid that this would provoke a reaction by the military government that would even result in IMPA being shut down. And as a result, the petition to the judge never got circulated. The idea just was dropped. And partly, of course, due to this, the effect of the repression on the Brazilian mathematical world. And in fact, I don't know if we've ever told anybody, but Alexandro came to Bahia and met with Steve, and I think Steve just wanted a witness to what they were going to talk to. They included me in the meeting, and Alexandro asked Steve not to go ahead with this petition because it might result in him losing his job and other acts of revenge that the system might plan. So actually Steve dropped the idea, and I think some people were sort of strangely thinking that Steve had somehow dropped the ball. So the meeting opened, and Mauricio Peixoto, who was a professor at IMPA and maybe one of the most dominant Brazilian mathematicians, and even I think at that time president of the Academy of Sciences, opened the meeting and said specifically, I remember very well, certain conversations will not be tolerated. So it seemed like, wow, this, any moment the military might come charging through the doors and take us all off. And so then after having made that announcement, he announced that Steve would be the first speaker in the meeting, and Steve got up, walked to the front of the room, took a piece of chalk, and wrote Alexandro Magalhães on the blackboard. in big letters. So I was sitting there thinking, oh my God, certain circumstances will not be tolerated, and Steve just did this very, I don't know, somehow this type of bold action on Steve's part in a very good and important way. It's Steve. He acts boldly, and somehow he's lucky, maybe, I don't know, but there's never been any serious negative consequences. So I was a little worried that this whole part of Steve's life wasn't going to be too represented at the meeting here. So I've told that story, and now you can find out more details by talking to Jair. Okay, so.
Can I add a comment, quick comment?
Yeah.
In the twist and turns of life, I can present a motion from the academic senate of the Brazilian university I'm retired from, the Federal University of Rio. They made a statement in behalf of the academic community of the United States that is under pressure of the Trump administration. So things turn around. Now Brazil lives in a democracy, and the United States in an autocracy, so to speak. So I refer to Professor Batterson to more details than I can provide. But I was a witness. I was a finishing master's student in that meeting, and all you said is what I witnessed to. And I thank, I am a good friend of Alexandre and his former wife, Dulce, and they are well now. They are very well. And I think that moment had an impact, although not explicitly, but it made Mauricio to be more attentive to what was going on. So I want to thank both of you.
Wow. Thank you. Thank you. Okay, mathematics.
You mentioned the new notices issue?
Oh, yeah, Indika and Jair have rediscovered Levinson's letter to Steve about the horseshoe. And they've told the whole story about how the correspondence took place, and it's all written up in the notices, and in fact, Levinson's letter has been found and printed on the cover. I've never seen a letter printed on the cover before, but it's printed on the cover of the notices. So you just might look at your copy when you get it and read their article. It's very well written, I must say. Any more comments? Okay. So so Steve was a topologist, and he came to dynamical systems, and there somehow should be a connection. And in fact, it's very important in the examples that he made, like the horseshoe, and this is a topologist working, and Steve, in fact, I'll mention more about how there's a connection between his earlier work and the dynamics in a little while. But I think that there was little in the way of connection between topology and dynamics before Steve got involved. Many of the tools of dynamics don't have a specific carryover to smooth dynamical systems. Topological systems, yes, maybe, but adding smoothness adds little to the understanding of the system. For example, the Lefschetz formula. Lefschetz formula tells you how many fixed points there are by counting the points with their index, and it gives you summation of -1 to the k trace of f on the kth homology group. So that's a formula that's valid in the C0 world, and smoothness has nothing, not much to do with it. And so what are the relations between these topological phenomena, or these topological tools, and dynamical systems, and especially smooth dynamical systems? It's these papers on smooth dynamical systems. So that's so I don't know, I had things here. I was gonna, let me first, I'm gonna talk about what I hope is correct. Work with Enrique Pujals and Axel, is Axel here? Axel Kodat is back there. And I think we finally got it in a case where smoothness is important for the answer and plays a big role in the phenomenon. So that's what I'm going to try to talk about today. The two notions are topological entropy and the map on homology of the induced map on homology of the diffeomorphism.
That's Steve.
That's me too. He's got Indika. I need my wife here, but she's not here. So, okay. So let me give you an example. It's the Lefschetz formula. So I just said what it should be. The Lefschetz formula should be summation -1 to the k, the trace of f star sub k on the kth homology group with real coefficients. And you sum that from 0 to the dimension of the manifold. That gives you the Lefschetz number of the map and homology theory. And the theorem is that that number is equal to the sum of the indices of the fixed points of f. Okay. So now that's, as with a lot of topological notions, it has a -1 to the k in it. So there's an alteration from one to the next. So I take some nice diffeomorphism with a bunch of fixed points, and the number of the fixed points is being told to you by this alternating sum of the traces. And then I product this diffeomorphism with this manifold with a circle, and I product the diffeomorphism with an irrational rotation of the circle. So what happens? There are no periodic points because the circle coordinate is irrationally moved and it never comes back to itself. So I started with this very nice diffeomorphism with a lot of periodic points, and I product with the circle, and instead of having a periodic orbit, I have a periodic circle. And on that periodic circle, I have an irrational rotation. So there are no periodic points anymore. So I've lost all the periodic point structure. What happened to the homology? Well, the homology got producted with the 0 and 1 homology of the circle, so Z and Z. And it's the same map in the two dimensions, but the -1 to the k. In one dimension is positive and the other one's negative. So it cancels out all the traces. So the Lefschetz formulas are zero, all of them, all the powers. So you started out with something nice, you product with a circle, and now you have something nice, but instead of fixed points, you've got circles. So why is that, a loss from the point of view of dynamics? There's no loss, there are these circles. So the Lefschetz formula disappears, but the homology didn't disappear, just the alternating sum. So in fact, the homology you used to have repeats in two dimensions. And so there is whatever action on homology is repeated twice. So can one somehow represent that action on homology in dynamics? And the sort of conjecture that's really sort of emerged from Steve's theorem at the time was that the maximum eigenvalue on homology should give you information about the topological entropy of the system. So before you had to take the alternating sum, so the maximum might have appeared in two dimensions and canceled out, which just happened when I producted with the circle. But it's there, it's still there, and now it's appearing in two dimensions. And in fact, what the conjecture was initially is that the topological entropy is bigger than or equal to the log of the modulus of the eigenvalues on homology, all of them. So this largest eigenvalue that we had before that was producing periodic points is now producing topological entropy in that same quantity. And so those circles are still there. So that was the conjecture, and it was sort of related to Steve's work in two places. One was he defined what later came to be called Morse-Smale systems, and these were systems with finite number of periodic orbits, each one of which was attracting all the points nearby for the sinks. So this was 19th century science, that things had equilibria, and the equilibria was stable. So that's what one looked for in chemical systems. And there was some work by Peixoto and two Russian mathematicians on studying such systems, and Steve came. Okay, so Steve came and made this generalization of those properties for all dimensions and all manifolds. And then he had, so I think we ran into each other one day in Rio de Janeiro, the same summer, 1971. And Steve said, "What are you working on?" I said, "Well, I was wondering about this property, structurally stable systems that had been hoped to be dense in the systems. It turned out examples of Steve and Ralph Abraham showed that they were not dense. So now what? So I was wondering if every system is isotopic to a Morse-Smale, to a structurally stable system. And we met on the street. It was a Sunday afternoon, actually. And Steve went off someplace on the beach. I went off somewhere else with my wife, somewhere else on the beach. And the next day, Steve had solved the problem. And in fact, he solved the problem with very much the same ways, or using some of the tools, let's say, that he used in the Poincare conjecture. So he managed to take a handle decomposition of the manifold and then deform the map so it preserved the handle decomposition, and in fact stretched the core and contracted the transverse disk so it was a structurally stable diffeomorphism, and you built the isotopy. So he solved the problem. And so then there was, also he asked the question about more Smale systems as to whether or not there was something beyond the fact that the Lefschetz numbers were bounded that you could say about a more Smale system. So in fact, the two questions are somehow related because the more Smale system essentially is preserving a handle decomposition that it defines. So, so there became this problem of whether or not the topological entropy of a map is bigger than or equal to the log of the modulus of the eigenvalues on homology. And then there were a bunch of examples. So more Smale was one of them. All the axiom A no psychosystems that Steve had defined were also proven to be examples of this, and a lot of other examples. And finally, Joseph Yamden proved the theorem that the inequality is true for C infinity diffeomorphism. And now the question has been open all this time. What about CR diffeomorphisms for finite R? And if I had, if I could show my slides, I might show you some pictures that would try to convince you that it's true for C2 diffeomorphism. So maybe that's, if the proof is true, I can tell you that when I gave Steve my thesis, he read it and returned it, correcting the English usage. I wasn't good at English. Corrected the English usage. And I said to Steve, you corrected the English, what about the mathematics? He said, time will tell. I can say the same about this theorem. Time will tell. Okay, I guess.
Any questions or discussion before we have a break soon? So I think one thing that came up here is the importance of Steve and Brazilian mathematics, both in terms of developing mathematics in Brazil, I think, given their stature, and where a lot of your own work and the controversies of doing mathematics on the beaches of Rio. As you can see, a lot of the mathematics was done there, right? Even though we had there were questions, I think, at the U.S. Congress about that. But in fact, the horseshoe, you found the horseshoe there and solved one of Mike's problems as well. Okay, so there's a break now, and I think we're resuming at what time?
11.
At 11? Okay, so there's food out there.